Hello and welcome to Fundamentals of Reinforcement Learning video series part 3. In the previous part, we discussed MAP-ROVER and R-Smart algorithm, and in this video we are basically going to implement this MAP-ROVER using this R-Smart in Python using NumPy from the very beginning. So just as a recap, the agent has to move in these 9 states, and the state 4 has negative reward, state 8 has positive reward, the other state has 0 reward, immediate reward. That's a Q matrix that contains initially 0 that we have to learn to come up with a policy, great policy. And the same kind of matrix will be a immediate reward matrix R that will contain at the 4th column it will contain -1 everywhere, and at the 8th column it will contain 1 everywhere, and the rest will be 0. The immediate reward matrix will stay the same over the iterations of the algorithm, but the Q matrix that will gradually change according to the equation that we saw in the previous video in detail. That is the Q update in R-Smart. So let's go to Jupyter Notebook and see how can we implement that. So first we import NumPy as NP because we are going to work with this NumPy. Let's build a Q matrix, which is np.empty empty 9 by 9 because we have total states 9. So yeah, so that, and then we have this Q. Everywhere we set a nan value, this np.nan nan value. So if you see that this Q matrix looks like the following. It's a matrix, it's a 9 by 9 matrix with all nan values. Now we fill this Q matrix, initialize with this Q matrix with zeros as described in this picture. So for example, for state 0, 0, 1 and 3, these indices, they will contain zeros. For state 1, 0, 1 and 2 and 4, these indices, they will contain 0 and so on. So let's fill this matrix like so, and the rest of the empty cells, they will stay nans. So Q at 0, we have only 3 transitions. From 0 we can go to 0, we can go to 1, we can go to 3. So initially that is 0. From state 1 we can go to state 0, 1, 2 and 4. So 0, 1, 2 and 4, and initially that value, Q value, is 0. That is just initialization. From state 2 we can go to state 1, 2 and 4 as described here. From state 2 we can go to 1, 2 and 4, 1, 2 and 5. From state 2 we can go to 1, we can go to 5, and we can stay at 2. So it is basically 1, 2 and 5. 1, 2 and 5, and that goes to 0. Similarly, from state 3, as you can see, we can go to 0, 3 and 4. So we have 0, 3 and 4, as you can see from the slide as well. Yeah. So from state 4, the possible transitions from state 4 is 1, 3, 4, 5, 7. So 1, 3, 4, 5, 7. So initially that is 0, just initialize that with 0. So Q at 5, from 5 we can go to, for example we can go to 2, 4, 5 and 8. Here we can go there, and this, that is 0. And from so 2, 4, 5, 8 for state 5. Similarly, state 6, we can go to 3, 6 and 7. 3, 6 and 7, and that is 0. And from state 7 we can go to 4, 6, 7, 8. 4, 6, 7, 8, and initially that is 0, and from state 8 we can go to 5, 7 and 8, 5, 7 and 8. Yeah, so that is basically the initialization. If you just see if everything works fine, this is the initialization that happens. And if you see this Q matrix here right now, if I just display the Q matrix in front of you, you can see that it has all the zeros where it should be, and the rest of the values are nans where the transition is not possible. Further, let's describe a reward matrix R, which has to stay the same throughout, which initially is Q, but the column of state 4 must contain -1 wherever there is a non-nan value. So idx is equal to np.isNan R 4. So that will give me the index of all nan values. So R at the complement of these indices at 4, they must be -1. And same we do with the state 8, because the state 8, it contains 1 everywhere. So 8 R complement of idx 8, it must be 1. So that's our reward matrix. If you see R is in the state 4, it is -1 wherever there is a non-nan entry, and in state 8 there is 1, and rest we have 0. So this R matrix will stay the same. This Q matrix will update according to the update rule that we saw here. Yeah. So that's the update rule, as we will see. So let's move to this updation. First, let's decide some maximum number of iterations. Let's say we have this max iter. Let's say we set this to 1000. It depends how many iterations you have to do. Number of states, num states, we have 9 states here. Eta, that is basically this value, eta. It is a hyperparameter. It is recommended, the practitioners recommend that this value should be less than 1, but really should be very close to 1. So eta is basically so let's set this eta to be 0.99, for example, here. Then we have let's start the algorithm. For each iteration, for each state, I sample an action and go to state j. So let's write that. For k in range max iter, sample an action. So before sampling an action, this is good to set this alpha value, and the recommendation is this alpha value over the time should decay. It should stay smaller than 1, but over the time it should decay. That's the recommendation. And one simplest rule is to just take it as a reciprocal of your iteration number. So let's define this alpha to be 1 over the iteration number, which is k plus 1. I'm just adding 1 because the k initializes with 0. So just to stay away from this 1 over 0 thing, that's the alpha. Then what I really do is, because I'm going to update this queue, I make a copy of it just to refer the old queue and the new queue. This is the copy. And now I define the probability of the probability of sampling a greedy action, or the action based on greedy choice. So let's say that is 1 minus let's say that is 10 divided by 20 plus k. So this is the probability. As you can see, this, as k increases, this probability also increases. So this is the probability of sampling greedy action. So as the iteration moves on and on and on, the probability of exploitation should increase, which is this probability. So with this probability, we are going to sample the greedy action. Otherwise, we are going to sample the non-greedy action at random. So select max false. This is if we really want to select the greedy action or the greedy choice. Initially it is false, and then we just see if np.random.rand, if this value is smaller than pk, then we basically select the greedy choice. Otherwise we will select the non-greedy choice. So here the greedy choice basically is if for example this is true, then we set this select max flag to be true. So that will indicate later on whether we have to select the greedy choice or we have to select the other. Now for each state, for I in range of num states, for each state, what we have to do basically is we have to sample the action. So first we sample the action from state I, the allowed states, which is idx, which is np.isnan, or we can pick this from R table, or we can pick this from the Q table. Either way, wherever is the nan, that is the non-allowable states, and the rest are allowed states. Then the allowed states are basically np.range num states and this idx. So this will give us the list, or basically the numpy array of allowed states, what states are allowed from index I, from state I onwards. Now what we do is we pick the j as the state which is basically the max. So j is q, I, from I what are the allowed states, and then pick the argmax of that. So which argument from these argmax, which argument is the max, which q value is the max? This is if we really use the select max. If we use the non-select max, then we have to do something else. So j is that. Now what we do is if select max is true, then j basically is allowed states j. It is that state, the j is the max state, else we have to delete this state, and we have to randomly choose one other state from the allowed states. So then allowed states is np.delete allowed states, and which state I want to delete, j. So after that, if this state has been deleted, then we have to move basically to, and we now have to pick a state just at random. So for example, j is np.random.permutation, for example, allowed states. So just pick a state randomly from the allowed states other than the state that is at max. So now j will contain the next state that we really are interested in. Now we know what is the next state. We know we are going to start from I. Now this is right time to update the Q matrix. So Q2, basically I comma j is Q ij, the old one, plus basically the immediate reward ij, plus eta. So let me multiply these etas and alphas afterwards. Let us just write this np dot nan max q from j to onwards. So whatever the maximum value is from q to onwards. So this is if these alphas and etas are not there. If alphas and etas are there in this particular way, then we have to multiply those factors as well. So let's multiply those factors. Here we have to multiply 1 minus alpha raised to the power k. So we multiply that. Then we have to multiply this whole thing. We have to multiply this whole thing with alpha raised to the power k, and we have to multiply this with this number as described in our algorithm. So we have to multiply this with that, and finally we have to multiply eta here with this, and that's the update of q. Once the q is updated for all these all the states, and if you see this code, it contains basically all the states and all the iterations and all the stuff, like, so all the states, all the iterations, and basically this is described right here. So we go for each iteration, for each state, we sample an action, and as we move on in iterations, the probability of sampling the greedy action becomes higher and higher, and that's how we decide whether, that's our policy, that we are deciding whether we are going towards the greedy action or not. So after that, this will be basically, this will have all the q updated for one iteration. After that, after this iteration, we have to set this q as q2, or if you really want a deep copy, you should call this copy function. Otherwise, even if you don't copy, you just reference, that's perfectly okay, because we are also copying here. So either way, that's fine. So if this code has no bugs, then it will train, it will run and update the Q matrix after 1,000 iterations. So let's see. For example, what it does. So I guess it has, yeah, it has no issues. So it runs properly. So let's see the Q matrix. If you see the Q matrix here, you have now different values. That is some positive values, some negative values, and stuff like so. Yeah. So if we now, for example, if we now sample our policies, what kind of, if we, for example, sample now, what kind of transitions should it take place if we start from, for example, if we start from state 0, what kind of actions, what kind of actions or what kind of states it visited. So let's set the num transitions. Let's set the num transitions to be 10 and see if we start from state 0, what are the states that it will eventually visit. So for k in range, num transitions, what we really do is we first print that now right now we are in state I, and then we sample the max index. np dot is nan from q from state I to that, and allowed states from that is np dot range num states. Num state is just 9 number of states, and we have this negative idx, that these are the allowed states. Now we have to pick the maximum state. So q is basically I, which is the state I, and then we have to go to allowed states, and we have to pick the max, the index of the maximum. And this j basically is allowed states j. So that's the next state. So we basically set this I to be j, I equals j, and then I will be printed again and again. So let's see for 10 iterations, if we start from 0, what transition our algorithm basically takes. So if you see, if we start from 0, it go to 1, then 2, then 5, then 8, which makes sense, it is avoiding 4. So if you see, for example, if you start from 0, then you go to 1, then 2, then 5, then 8. Yeah, so it's working perfectly fine. And once it is in state 8, it learns to stay in state 8. Yeah, it is just for 10 iterations, 10 transitions. If you move the transitions to high, it will, for example, it will stay in 8. Once it is in 8, it learns to stay in 8. And further, it basically learns to avoid state 4. Yeah, it does that. So yeah, that's the code. That's a very, very simple example of MAP-ROVER that I have implemented in NumPy for, completely from scratch. It has other notions as well, average rewards, discounted rewards. There is a actor critique method as well. There are so many methods. I've just given you a flavor that how our MAP-ROVER learns to visit different states. If, for example, we start from if we start from state 3, for example, let's see what transitions does it make. From 3 it goes to 0, then 1, 2, 5, and then 8. Again, you can see it is avoiding state 4. If, for example, and by the way, if we set that the number of transitions to go to state 8, if the MAP-ROVER will die quickly, if it doesn't reach to state 8, if we model that in our code, then it will not go from 3 to 0. It will directly go from, it will learn to go from 3 to 6, 6 to 7, and then to 8. Yeah. So if, for example, you go to, what if you start from state 4? If you start from state 4, if the MAP-ROVER just lands at state 4, what should it do? Well, it quickly go to 1, then 2, then 5, and then 8. Yeah, it learns to do that. Yeah, the learning can be made different, or the result might be different if you play with these hyperparameters, alpha value, this value, the probability of selecting the greedy choice and stuff like so. And you can play with that. You can make it more fancier. You can actually have a record of average rewards over time, over transitions. You can display that and stuff like so. And yeah, so that's it. Hope to see you next time.